All right, so our topic today is angles in standard position. In quadrant 1. So let's go back down memory lane for a moment and remember what we learned about trig in grade 10. All right? So what were the 3 trig ratios that we learned about? Hannah?
Or just kidding.
Well, SOHCAHTOA is how we're...
That was a great joke.
Forget about it. SOHCAHTOA is how we remembered the trig ratios, but what are the actual trig ratios? Justin?
Sine, which is opposite over.
Okay, well, just tell me what they are. You always...
Sine, cosine, tangent.
Thank you, thank you, thank you. All right, so sine, cosine, tangent are our trig ratios. And to understand what they are, we drew ourselves a triangle, ABC. And how would I name the side that I've marked in yellow? What would be the name that I would give that side? Lowercase a, right? So the vertices, which are the points of the triangle, are capital letters, and the sides are lowercase letters, and you name the side by the angle that's opposite. So the one here on the bottom would be B, and the one across from C is C. All right. So if I'm focusing in on angle A, then the side across from angle A is given what label? Opposite. So this would be the opposite. And what's the one that's beside it? Well, actually, no, let's do the one across from the right angle first. What do we always call that? That's our hypotenuse. And the one that's beside it but is not the hypotenuse is called the what? Adjacent. Good. All right, so now we're ready to talk about the sine, cosine, and tangent and what they mean in relationship to this triangle. So the sine of A is what 2 sides? No, you should just remember it. Opposite over hypotenuse, that's right. This thing, recording seems to make my pen delay, which is already driving me nuts. Anyway, so opposite over hypotenuse. It's the ratio of those 2 sides in that order, right? What is cosine? Yes? Correct. Adjacent over hypotenuse. And finally, tangent. Huh? Opposite over adjacent. So that's how we learned the trig ratios last year. We learned them in terms of a right triangle. This year we're going to expand beyond right triangles because not all situations can be drawn in a right triangle. All right? So the trick that we're going to learn this year will allow us to work with triangles of any shape, okay, not just right triangles, but it will also allow us to do trig on angles that are greater than 180 degrees, which of course would never fit inside a triangle, right? Because all the angles in a triangle add to 180. You could never have an angle greater than 180 within a triangle. So we're going to shift our thinking from the ratios of being the ratios of sides to look at how they relate to each other as a point in the coordinate plane. So that's the shift that we're going to make in our trig this year. It sounds complicated, but it really isn't. Uh-oh. Oh, keep it just the same, and don't show me that. All right. So everybody remembers this part, though, right? From your last year? The trig was usually the chapter that most people did quite well on. All right, the other piece of review that I wanted to look at, and we talked about this a little bit last chapter, was the naming of the quadrants of the coordinate plane. So we know that the coordinate plane with our y and x axes cuts the two-dimensional plane into 4 pieces, or 4 quadrants. Where is quadrant 1? Justin?
Up the right-hand side where x and y are both positive.
Beautiful. What a lovely explanation. All right, so quadrant 1, upper right side, x and y are both positive. Excellent. Now, which way do we move to get to quadrant 2? Counterclockwise, exactly. So this is quadrant 2, this is quadrant 3, this is quadrant 4. So today we're going to focus in on just quadrant 1, just to get the basics around what we're doing with and making that shift from the ratios being ratios of sides to ratios of values of points in a coordinate plane. Monday we'll expand and we'll look at how it works in all 4 quadrants. All right, let's start with an example, real life example. A boat is 80 kilometers north and 30 kilometers due east. Should have due north in there as well, I guess. Of a port. How far is the boat from the port? So if you wanted to solve this problem, this is actually a grade 8 problem, but that's okay. It's going to make a point. How would we set it up? What would you do first? I'm not going to draw a triangle necessarily, but I am going to draw a picture. Okay? So I have my port here. And which direction of this north? We do a lot. Trig is used a lot in navigation, so we need to know our directions. So which way is north? Up. South, of course, is down. And east and west, which one's to the right? East. 50-50 chance. And west is to the left. Okay, so if I am 30 degrees to the east and 80 degrees to the north, if you think of the directions here, then I'm 80 kilometers, I said degrees, I meant kilometers, 80 kilometers north and 30 kilometers east, so that means my boat is right here. And I want to know the distance from the port to the boat. So now I have a picture. It's always easier to do trigonometry or any of this kind of work with a picture. All right, so how can I find the distance from the port to the boat? Absolutely, do Pythagoras. So what I'd like to do is think about this being a right triangle. This distance, of course, would be 80. This distance here would be 30. And let's say that the distance that we're looking for is x. So x squared equals 30 squared plus 80 squared. So 900 plus 6400. So x is equal to the square root of 7300. And this is irrational, so all we can do is give a decimal approximation. 85.4 kilometers. So I just did this to emphasize that we can think of B as a point on a coordinate plane. We don't really need to think about the triangle. We're going to use the triangle initially to figure out what those relationships between all the pieces are, but eventually we're going to move away from that triangle. All right? So you can think of B as being at the coordinates 30, 80, right? Because you're gone over 30 and you've gone up 80. All right, so let's put this into general terms. So we have our coordinate plane, and we have our point P that has the coordinates x, y. We always use excuse me, O to represent the origin, right, which is where the two axes intersect. And I'm going to draw my distance from O to P. And I'm going to call that distance r, lowercase r. Now the piece that I'm going to add is angle theta. Now theta is a Greek letter we use all the time to represent angles. All right, so rather than using A, B, or C, because we don't really have a triangle anymore, so we can't use the letter of the vertex, which we've used in the past, we'll just put theta in the actual angle, and that's how we'll identify the angle. Now, theta is being measured from the positive x-axis up to the line segment between the origin and our point. All right, so this is the same kind of scenario, right? O would be the port, P would be the boat. And if we wanted to find the angle that the boat was actually moving in when it was going from the port to where it is, we could have calculated that. We could have used trig to calculate that, right? So let's start by determining. No, sorry. Let's do it this way. How can we write r in terms of x and y? So I want to write r as an expression using x and y. How could we do that? Just like the last question, isn't it? Isn't r like x? Okay. X and y would be 30 and 80. So we don't know what x and y are. That's okay. I just want to express r in terms of x and y. Yeah? Yeah, beautiful. So r is equal to the square root of x squared plus y squared. Right? Just Pythagorean theorem. We can think of our right triangle. Right? We can drop a line down here, make a right angle there. This distance is y. This distance is x. So we can find r by using good old Pythagorean theorem. All right. How can we write angle theta in terms of x and y? So now we want to write an expression that uses the angle of theta and x and y. Or not. How could we do that? Again, think of your right triangle for now, because we're going to use the right triangle to help us define each of these relationships. And then once we know what the relationships are, we won't need to think about the right triangle necessarily. You still can if you forget and you want to go back and sort of develop them yourself. So can anybody write theta in terms of x and y? Yep. Wow. Okay. That's great. Okay, I'm just going to write it this way to start. The tan of theta equals, so tangent, remember, is the opposite over the adjacent. Okay? So that's tan of theta. Justin took it one step further, which was awesome, and said angle theta is equal to the second function tan of y over x. That's beautiful. That's awesome. So he's gone all the way to actually finding the value of theta. Yes?
Arctangent.
No? No. Oh, well, do we call it arctangent? No, let's not go there. Okay, so we're just using our calculator if we were going to do it. That's how you get backwards from the ratio to find out the angle. All right. Now let's see if we can write the x-coordinate in terms of r and theta. So how can we write a relationship between x, r, and theta? So instead of using x and y, now we're going to use x and r. So how do x and r relate to the angle of theta? Anna? Laura? Beautiful. Okay, cosine theta equals x over r. You're absolutely right. So that's how cosine theta, x, and r are related. Could we simplify that and write x by itself? How could we shift those pieces around to get the x by itself instead of the cos theta by itself? Skylar? Well, we want the x by itself. So if you think of cos as being over 1, then x times 1 has got to be equal to r times cos theta. Right? Yeah. It's just a proportion. So we're doing the cross products of a proportion are always equal. So x is equal to r cos theta. And the last one, you can guess, we want to write the y-coordinate in terms of r and theta. So how can we do that? Yep.
Sine theta.
Thank you. Sine theta equals y over r. Right, so then y would be equal to?
Sine theta times r, or r times sine theta.
Yeah, doesn't matter. But we'll do r sine theta. You got it. So we could, if we wanted to, think of this point P, instead of being x, y, we could think of it as r cos theta, r sine theta. Right? Because that's another way of thinking of x and x and y. So you could find the coordinates of that point if you knew r and you knew theta. You can find r if you know x and y. You can find theta if you know x and y. So they're all connected. Okay? All right, so now we need to learn some terminology. So So if we have a point P, x, y, in the coordinate plane, then R, so R is defined as the distance from the origin O to the point P. Which has the coordinates x, y. So r is the distance. Remember that. That's important. It's the distance from the origin out to the end of that point, or out to that point. So you draw a line segment from the origin to P, and the distance of that line segment, or the length of that line segment rather, is what we define as r. Okay. Now, OP is called the terminal arm. So we call this the terminal arm. And P is called the terminal point. That's in relationship to angle theta. So angle theta is said to be in standard position if it's measured from the positive x-axis counterclockwise to the terminal arm. We restrict the value of theta in standard position to be between 0 and 360 degrees. Okay? So, this is important. Let me explain it a few times. So when we're measuring angle theta, we're always measuring from the positive x-axis until we hit that terminal arm. That is theta in standard position. Because we can do all kinds of angles in a coordinate plane, right? We could go from the positive x-axis going clockwise until we hit the terminal arm. That would give us a completely different angle, right? We could measure from the positive y-axis to the terminal arm. That would give us a different angle. We could measure from the negative x-axis to the terminal arm. That would give us a different angle. So in order to be consistent, we had to agree upon one way to measure an angle, and we call that particular way, that angle in standard position. So it's understood that when you're told that an angle is in standard position, that it's being measured from the positive x-axis up to that terminal arm in a counterclockwise direction. The reason that we restrict it between 0 and 360 degrees is because if we move counterclockwise, we could get there if we went 1 and a bit rotations, or 2 and a bit rotations, and so on. So again, there would be multiple angles that would end on that terminal arm. We need there to be 1. Okay? So we describe that angle in a very particular way, measured from the positive x-axis up to the terminal arm counterclockwise. That angle is in standard position. So when we do all of our work, we're working with angle theta in standard position. And it'll state that in the question so that we're clear on how we're measuring that angle. Okay? Because there's lots of ways that we could get to that terminal arm, and we have to pick one. Questions so far? So hopefully you can see that when we start defining sine, cosine, and tangent in terms of x, y, and r, that we can now have angles of any measurement. Right? We can have angles from 0 degrees up to 360 degrees and beyond if we wanted to. We can have negative angles. We can have, if we were to have an angle over in this quadrant, what's the type of numbers or values do x and y have in quadrant 3? They're negative. So if we thought of them as sides of triangles, it wouldn't make any sense. We can't have negative lengths of triangles. So that's why we have to stop thinking about trig in terms of right triangles and start thinking about it instead by the value of its coordinates. That will make more sense as we continue through this chapter and we start doing more types of questions. But that's why we're picking coordinates as a way of defining trig instead of right triangles, because it allows us to get way more angles and do way more with it. All right? Okay, so let's do an example. Put this into practice because I think it'll make it a little clearer for you. So the point P, 4, 6, is on the terminal arm of an angle theta in standard position. So you can see why we had to go through that vocabulary, because that's the way a question is going to be stated for you. We need to be that precise so that it's clear exactly what we're talking about. All right, see if you could draw me a picture of what that question is stating. Draw me what that would look like. Okay, so your picture should look something like that. You've got P in quadrant 1 at a point that looks approximately like it's 4, 6. We don't have to be precise, but we do need to kind of want to be in the ballpark, because that'll just give us an idea of whether our angle makes sense. It's a reasonable answer based on where that point is in the plane. And O and P are labeled and theta is labeled, and you notice that I labeled it, showing that it's in standard position by moving from that positive x-axis up to the terminal arm. All right, so here's what we're going to do with this. First, we are going to determine the distance r from the origin to P. So how are we going to do that? We're going to find the distance from the origin out to that point. Justin?
We defined previously that r equals the square root of x squared plus y squared.
Good.
So we can plug in x and y, which in this case is 4 and 6, they're r.
Beautiful. Okay? So, we already defined it, as you said. R is the square root of x squared plus y squared. Okay, that's why we did that work initially. And so we just need to plug in the values. So there's really not much to it. So we get 16 plus 36. So r equals root 52. Do you think we'd leave it like that? Nope. What would we do? Yes? Leanna?
You can mix it.
Yes, you can simplify it. Absolutely. So we can take a 4 out of there, so this becomes 2 root 13. Now I want you to leave it in exact form. Okay? So here we get to practice our radicals again in a different way. It's important to leave it in exact form because we're going to use that value, or we may use that value, to find the measurement of the angle. And if we round it off, because it's an irrational number, then we introduce error into our final answer. And our angle may be off a little bit, depending on the precision in which we're asked to give the measure of that angle. So we will always work with exact values, not decimal approximations, as we have throughout everything we've done so far. So it hasn't changed. Okay. The next thing that I want you to do is to determine the primary trig ratios. And I'm just going to put a little note here. Primary trig ratios are sine, cosine, and tangent. I know you think those are the only trig ratios, but there are the inverse trig ratios that you'll get to look at in grade 12. So primary trig ratios mean sine, cosine, and tangent. Now, remember in chapter 2 I said, it might be really nice to have a little index card and have all the perfect squares and all the perfect cubes on it until you get more familiar with them. So here's what I would put on a index card for trig. I would draw myself a little picture. I'd put my point P out there. I'd label my R and my O and theta. I would say that R is equal to the square root of x squared plus y squared. And then I would put on the 3 primary trig ratios. So remember we said the tan of theta was y over x. The cos of theta was x over r. And the sine of theta was y over r. You'll use those quite a bit in this chapter, so probably by the end of the chapter you won't need that index card anymore. Although we're going to add some new stuff to it next week as well. But that would be my little trig cheat sheet for now. Okay? To help you just remember those ratios. Because it's that simple. Just like we learned SOHCAHTOA to help us remember the trig ratios when triangles were involved, we have to know these as well. And you can, if you forget, you can go back and draw your right triangle and you can figure it out again from what you know from grade 10. All right? As I say, I think you'll probably start remembering it pretty quick. All right, so in this case then, what would tangent of theta be? Scott? 6 over 4, which reduces to 3 over 2. Okay, what about cos theta? Okay, Skylar, you're on a roll. 4 over 2 root 13. And we always reduce to lowest terms. Now, in the past, I've always made you rationalize the denominator when you have a radical. I'm not going to be too picky in trig, to be honest, because we're using the trig ratios to help us find other stuff. And it's not really crucial that we have them in proper form. So I'm quite happy to accept just 2 over root 13. But you might, in your book, see 2 root 13 over 13, which of course would be the same value with the denominator rationalized. So you may see either answer in your book. I'm not sure how they write them. But for me, I'm not going to be too concerned if you leave it as 2 over root 13. Okay? And then the last ratio, sine theta, will be? Huh?
6 over 2 root 13, which goes to 3 over.
Perfect. All right, so 3 over root 13. Okay, the last thing that we're going to do is determine the measure of angle theta. Everybody's familiar with the symbol for angle? It's kind of like an L squished up a little bit. Okay? You know that we like to write things as short as possible in math, so this can be written simply as m angle theta. So if you see m angle theta, that means measure of angle theta. So if it says find or determine m angle theta, it means find or determine the measure of angle theta. So how many degrees it is. All right, so how are we going to do that?
Is this when you use like your camera, which like the -1 and put in the measurements that we have?
Yep.
So if you need, I guess that would be.
We got 3 trig ratios. Does it matter which one we use? Nope. We could use any of the 3 of them. It really makes no difference which one we use. If I was going to put this into my calculator, I would probably use 10 because it doesn't have any radicals, so it's just a little bit easier to type in. But it doesn't matter. All right? So we would go 10 to the -1 of 3 over 2, and we put that in our calculators. So second function 10. 3 divided by 2, excuse me, and we get 56.3 degrees. So, everybody get that? Remember how to do that on your calculator? Yes? Say that again. Oh. Yes, I believe the homework. I think I put the homework up for this chapter, but if not, I will before I leave.
Okay,
Thank you. You should probably use this to sign out, eh? Ooh, you're late.
Thanks.
Go. There you go. Thanks for being patient. Anybody not get 56.3 degrees? Okay. That means that your calculators are all in degrees. If you didn't get 56.3, it means your calculator is not in degrees. So, anybody want to tell me now? Did they not get 56.3 degrees? So, if you need to change the mode of your calculator, with the graphing calculator, click the mode button. You'll see that it's the 3rd on the list. Just go down to that, over to degrees, and then press enter. And now you'll be in degrees. Okay? So, you want to make sure that you're in degrees. You'll notice that the other option, of course, is radians. Next year, you're going to start working in radians. And it's just another way of measuring angles. So we measure angles in degrees. So we have 360 degrees that make up a full circle. When we're working with radians, 2 pi is a full circle. So we just work with ratios of pi to measure the angle. And of course, pi is related to circles. So we start thinking about measuring angles in terms of where they would be on a circle. So that's what you're going to start looking at next year in Pre-Calc 12. All right. Let's try one. So the point P, 5, 2, is on the terminal arm. of angle theta in standard position. So basically I want you to determine r, which again is the distance from origin to P. Determine the primary trig ratios. And determine the measure of angle theta. So find those three things for me. All right, let's see how we did. Shh. Quiet, please. Okay, so our picture over 5 up 2 looks something like this. So there's P at 5, 2. Here's R. Here's theta. Here's the origin. So R is equal to the square root of 5 squared plus 2 squared. Okay, guys, please. So 25 plus 4, root 29. So tan theta, which is y over x, will be 2 over 5. Cos theta, which is x over r, is 5 over root 29, and we can just leave it like that. And sine theta, which is y over r, is 2 over root 29. And I would get in the habit of just writing out what that ratio is every time, because every time you do that, it's going to connect it back to your brain, and pretty soon you're going to remember that. So I just get in the habit of writing them out each time. So then the measure of angle theta, we can pick any of these ratios. I'm going to use tan again just because I don't have to type a radical into my calculator. And 21.8 degrees. Yes? Everybody able to do all that? Make sense? Pretty easy, right? All right. Just a couple more things before I let you start working. Trig is used a lot in navigation, because when you think about, especially if you're out on, say, a boat, you're out in the middle of the ocean, trying to find a point or a direction that you're going in, it's hard to define that because you're not on a road. There's no specific route, right? So we use trigonometry to help to find where we are or what direction we're going into. So anybody here done any navigation? Figured out where they're going on a chart? Okay, so you familiar with bearings?
Yeah.
Okay. I hate bearings personally, but bearings is one way that you can describe a direction. So basically with bearings, due north is 0 degrees, and then it's clockwise, right, as you're moving. So if you're going 40 degrees, you're basically going 40 degrees east of north, and that would be the direction that you'd be moving in. So that's one way to do it. The other way that they talk about in the book is kind of a shortcut of that, I guess, or another way of describing it. So they talk about headings in some of the questions like this. Maybe you're going west, 50 degrees south. So remember, north, south, east, west are our 4 directions. So if I'm going west, 50 degrees south, then I'm heading in a westerly direction, but I'm adjusting my course 50 degrees towards the south. So this is the actual direction that I would be moving in. Okay, so you start with the first direction, in this case west, and then you move however many degrees it states towards the other direction, in this case south. So see if you can draw what this would look like. East, 30 degrees north. Which direction would you be heading if you were traveling east 30 degrees north? Just sketch me a little picture of that. Okay, so we would be starting by going an easterly direction, and we would adjust that easterly direction 30 degrees towards the north. So our overall direction would be as shown. Okay? So there's some questions. We don't have a lot of time left. I want you to get started on this so you can do a few questions. There's a few problems where you have to work backwards from R and theta to find x and y. But I'm confident you guys will be able to do that. So give it a shot, and then we'll talk about this some more on Monday. So I'd like you to do page 431 to 437, numbers 3 to 5, 7 to 13, and 16. And we'll take those up on Monday, and then as I said, we will continue the same kind of work into the coordinate plane. Other coordinates, or other quadrants.